Okay, the next speaker is Professor Min Chi from NC State. So Dr. Min Chi is a professor in the Department of Computer Science at NC State University. She earned her PhD and MS in the Intelligent System program from University of Pittsburgh and a BE in the Information Science and Technology from Xi'an Jiaotong University, China. She was a postdoc fellow at the CMU and Stanford. Dr. Chi received 10 Best Paper, Best Student Paper, and Outstanding Paper awards. Prestigious Aloha Foundation Engineering Research Achievement Award, and the NSF Career Award. Her research areas include AI, deep learning, and reinforcement learning frameworks tailored for addressing human-centric challenges across diverse domains. Her expertise extends to real-world settings such as education, healthcare, nuclear power, and humanitarian efforts, including food banks and disaster relief. In her keynote, From Internet to Impact, Designing AI for Human-Centered Decision Intelligence, Dr. Chi will discuss how AI will empower human decision-making in fields like education and healthcare by aligning intent with real-world outcomes. So please welcome Professor Min Chi.
Hey. Good morning, everyone. My name is Min Chi, and I am working for Computer Science Department. And today I'm going to share some of the research my student and I have conducted in our lab. So first of all, our lab is focused on what we call kind of human-centric tasks. Okay, so here is some of the system we have worked on our projects. And we work on a lot of intelligent tutoring systems for probability in my lab and the logic tutor and also programming. And we also work on the healthcare involved like 3 large healthcare system and on sepsis prevention and nuclear control. And we are collaborate with the national lab on how to control the nuclear reactor safely in the simulation, of course. And the last one we working on real world is very messy, is the food bank. And we have worked on 2 large food bank. One is our North Carolina food bank, and another one is the California food bank, which actually cover 2 different disasters. We have hurricane and they have wildfire. So what is common in all these tasks? What we can think is all these tasks is kind of a temporal sequential decision process. Each dot is a timestamp about the current state, and the human will involve some of the decisions, and then the whole state involved into the next state. Each of the dot here has a lot of challenge. For example, the data can be missing for healthcare, the treatment, and we can monitor and test the patient all the time. In the healthcare, we have 80 to 90% of the data missing all the time. And also human data collection is noisy. So each of the dots looks like we observe them, but there's noise, there's uncertainty, and also there is missingness involved, data quality. And the other task is human make decisions, right? A lot of things in these tasks are high stake and high risk. And we do not always want AI to decide everything. We know we have experts. How we can involve the human knowledge into this process is another thing. We want AI to be transparent, we want interpretable, and we want to trust the AI decisions as our opening have mentioned. So there's a lot of concerns in these domains. So in the core of my research, I phrase it is like H core, and H is human-centric. Fundamentally, we want everything to be human-centric about our humans. And the core in the C part is complex data. Our data is noisy and mislabeled. And if we know supervised learning, it's all learned from the label. If the label is not trustworthy, what we can do about it? And then the O represents optimization. And fundamentally, a lot of tasks we think AI is good at optimization, right? And the modeling, without modeling, we can't do a lot of things about trust optimization results and so on. The last most important is the evaluation. Whatever we can say about our model is fantastic in paper, how we evaluate in the real world? Is that really going to make an impact on the outcome we care about? And so my work today, I'm going to primarily focus on reinforcement learning because that's the passion and for the kind of since my PhD. And in the reinforcement learning, people who probably we heard a lot of reinforcement learning, the fundamentally reinforcement learning is about how you make a decision at any given state to maximize some type of reward. So we have state representation, we have action, and we also have a reward. And this kind of reward, we want not only short-term reward, we want long-term reward, right? And so reinforcement learning has been successful in a lot of gameplay, like Atari games, and also AlphaGo. We win the world champion about the game Go. That's why reinforcement learning become very popular in these days. And so when we do reinforcement learning for this high risk, high stake, what we do is we can't interact with the patient or student as we train our policy, like what we do on Atari games. And what we can do here is we have some historical experience data we collect and we do offline. We try to induce policies from this part of data we have. And once we induce policy, we try to evaluate the policy based on the historical data. If we know machine learning is once you have a policy you carry out, there is a population or distribution shift. And the goal here, how you evaluate the policy reliable on using the historical data. That's a lot of statistic questions, and hopefully people here have gave us some insight as well. Okay. So the biggest challenge here is oftentimes everything looks really good when we run on Atari games and we run on our historical data. We induce policies supposed to perform very well. But when we evaluate in the real students, sometimes evaluate on healthcare, we can't, right? But on real students, oftentimes we can't get significant. That's all we care about. And if you have some of the intervention, you said it's great, but you evaluate in the history in the classroom study with controlled and random assignment, the result is better, but not significant. That is cost a PhD student dissertation. And so the goal here is how we can close that gap. Whatever we say, it's going to work, and it's going to work in real life. And also, more interestingly, we need to think about why it did not work in real world. And it's probably because whatever we model, we actually do not encounter the human complexity, right? We have our own reward functions, like the Atari, it tried to get the score, but the human, we maybe want fun. We maybe want to learn very efficiently. So reward function is much more complicated in the real world as a human versus the Atari assign a score. And also there's a lot of state observation that most of the Atari games have the screen of the entire gaming, but for each of us, all I observe is you are here today. I don't know the rest of the history or background or what you're thinking about, right? So it's partial observable. And so the goal here is how we can rephrase some of the framework of the regional reinforcement learning for human-centric tasks. And in this talk, I'm just saying that right now our lab is working on this, what we call the human and AI interactive reinforcement learning framework. In this framework, we can think that we have the environment, whatever the environment is, and interact with the human. And this human can be student, can be patient, or can be the patient or the physician. They have their own intention, they have their own strategy making decision. And our reinforcement learning agent is running backend. And we will model what is the patient human's decision-making process, what they try to achieve. And the AI agent, whether to check this kind of policy is well conducted or carried out. And if there is a critical moment that we know human is failed, we will try to intervene by prompt or nudge the human saying, you probably should consider these options, and here is why. Okay, so that's our overall framework. And we'll start with some of the challenges from the original reinforcement learning framework and towards today's this human and AI interactive framework. So first of all, the system we have used is two educational systems. Here's their interface. And the three healthcare systems we used is Mayo and Christine can CCHS and also mimic data. That's kind of in the standard machine learning and AI field. You always have a public available data, and everyone use mimic data. And so we focus on one disease called sepsis, and septic shock is very deadly. It's the most costly in the US kind of healthcare system. It's constantly increase as well. And our goal here is try to model disease progression and also prevent sepsis. And sepsis, another symptom, is very early symptom, is very subtle. It's very hard to detect. But early detection and treatment can basically prevent people from death. And so in the first reinforcement learning framework, our tackled is primarily in the real world, reward function is much more delayed and not observed until the end. So for example, you can have some early treatment or kind of a boosting, but the patient feel recovered at that moment does not mean the outcome is good, right? So our goal here is saying we want the patient to be out of the hospital and do not return back, and in the next 2 weeks. So we have this long-term rewards that we want to achieve, and short-term reward is we want to maybe boost, but the short-term reward may not kind of influence the long-term reward. And so first work we have done is how we care about long-term reward, how we can infer the reward along the trajectories. In terms of the treatment, we can think in every step, there is reward available, but we can not observe it. And the goal here, how we can infer this reward from long-term outcome and by make them available for the reinforcement learning agent, because reinforcement learning agent do not act well when you do not have a reward function constantly guide the agent to learn. And in this work, we first using Gaussian process, try to infer the reward on every step. Basically, you distribute the big ending reward along the trajectories. And then we tried on the Atari games, and it's pretty successful. And here is some examples that we try to make. The story short is our inferred reward is act as well as the ground truth immediate reward that we know in Atari games it's available, but generally much better than the delayed reward. Once we pump the reward function with noise, because human generally have noise in the reward function, our inferred reward works much better than the immediate reward. And we evaluate the results in the two systems. One is the education, one is healthcare. And the story is here. Once we infer the reward, we find we induce policy much better. The treatment agree with our policy, the death rate is much lower. And so the next one is the decision is we want to, so far the reinforcement learning is assume we give the agency all the power. They make all the decisions for us. But we know as a human, we are sometimes good at making decisions, and also we are highly motivated to make decisions. That's what we define like freedom, the choice, right? We want to make sure that we have the choice to make decisions if we want. So there is a lot of literature on the benefit of the human making decisions, but how we can incorporate these human decisions into the framework. So we kind of propose this, what we call the human and centric decision-making process. So in this process, the human interactive is the environment, and then human making decisions, and the AI RL agent is making it in the background. And we constantly model the human decision. So first one, our goal is to say AI agent should not interfere with the human decision making unless it's critical. So how we define critical? That's one of the questions. We don't want to constantly interfere with the human decision making, but how we define critical decision moment. So in this work, what we have motivated from animal behavior to say what is the moment we define as a critical moment. In the animal behavior, there are two things we learned. It's first, you define a critical moment decision point when the decisions on that state make a difference in the long-term outcome. That's what we call the Q value difference. It means if in this state, you take two different actions and their outcome will be large different, then that state is critical. The second state is also from animal behavior. If this state, I'm going to get a cheese, that is a critical state. I should really go for that cheese immediately. And so we're using this kind of motivation and developed what we call a long-short reward framework. And the long-term reward is come from the Q value that any Bellman from reinforcement learning will give us. And the reward is come from the infinite or inferred reward from the first work we have done. So in our critical policy, here's the result. We first determine, is this state critical? If it's critical, you will carry out optimal actions. If it's not critical, carry out anything you want. Okay, so if we evaluate this one on the healthcare system, and here's the things we compared with physician's policy, that's in the middle. The last one, a deep reinforcement learning, that's kind of at that time the state of art. Everyone used deep reinforcement learning. And here, the gray bar is represent if the policy disagree with my policy, my induced reinforcement learning policy, whatever, and what is the y-axis death rate, okay? So you can see the red bar is the 10% of the trajectory agree with the policy, and their death, like a septic shock rate is really low as expected, right? If your policy, you carry out the trajectory, agree with my induced policy, that means the physician did a good job if my policy is effective. And their death septic shock rate should go down. And when you disagree, then the septic shock should go up. And so you can see this is verified the reinforcement learning, you can model how the physician make decisions. And as expected, that the most familiar agreed policies, patients have less septic shock rate than the least agreed trajectories. Okay, any questions? So next one is we also evaluate this one, the critical policy on the healthcare system, on the Mayo healthcare. And here we also compared like 3 policies. First one is our critical one. And in the middle is the, I think in the middle. In the first, it's the overall trajectory. In the middle, it's the shock patient. In the left, it's non-shock patient. And here we have 3 bars. The first one is our critical policies. The second one is the expert. And the last one is the deep reinforcement learning policy. And here what we say, the gray bar represent all the decisions that the reinforcement agent has to make. Because the critical moment policy only make a decision on critical state. That's why the gray bar for critical policies is lower. But on the other, for physician policy, deep reinforcement learning is constantly making decisions. That's why the gray bar is 100%. Does this make sense? So all the states, they will make a decision. For critical policy, they only make a decision on critical state. That's why the gray bar is lower. And then the second thing you may notice is the ones, what is the color is in the shock patient, and the CQL interfered with the human decision much less than the DQ and the physician policy. Okay, and additionally, in the non-shock patient, that CQL even less interfere with human decisions. That means the non-shock patient, actually, physician probably did mostly correct, that the critical policy don't need to interfere with human decision-making. But in the critical state, in the shock patient, that CQL are more likely to interfere because sometimes maybe physician missed it. Okay, this is a Mayo Clinic, and Mayo Clinic is one of the best healthcare system we know, right? And I will show another result. It's from a healthcare system. I'm not going to name it. And you can see this healthcare system, everything shoot up. And you can tell that this healthcare system, that even with shock patient, that all the policy will constantly interfere with the decision. So you basically saying the human decision may not be optimal. And this result for non-shock patient is lower, but for shock patient shoot up a lot. So this kind of things make us to see that reinforcement learning can be used to assess or help that physicians or humans to make decisions in real world, and especially to improve the outcome. So far, we're talking about these decisions in terms of assess human, but more importantly, how we can help human to make better decisions, right? And in this case, how we can say that we want to interfere or nudge the patient, the human make decisions without just saying you should do this. We should give them a good reason. And a good reason should be kind of tailored to human thinking. So you can't just say, let's do this because blah. And you should say, I know you are thinking about this, and let's do this that help you to achieve the same goal you want. And so the goal of the third one, interactive, is we try to model what is the human are thinking about, what is their reward function, and generate an explanation that tailored to the human's thinking process. So first of all, we want to model humans' decision-making process. We use what we call the apprenticeship learning. And as we can see so far, reinforcement learning is all about optimized reward function, right? Reward function is determined like the label for supervised learning. You learn what is cat, what is dog by labels. Reward function gives the reinforcement learning all the signals they try to optimize. But the reward function design is very hard. When we design sepsis, can you give a value for life, for live, for death? Can you give a value for you are getting treatment or you are out of the hospital? You quantify that process itself is a very challenge. And so apprenticeship learning advantage is I do not need predefine a reward function. I look at the expert design kind of a decision process. I infer what is the reward function they are considering. And once I infer the reward, I can induce policy as a normal reinforcement learning process. And additionally, apprenticeship learning is very data efficient. So for deep reinforcement learning, we need millions of the data trajectories. Apprenticeship learning, we need 18, much shorter, but we need a higher quality. We need to make sure the demonstration come from the expert or close to expert. So that's kind of what I'm trying to sell here, apprenticeship learning. That is our human expert can demonstrate, contribute to this process. But original apprenticeship learning, most of them are online. You learn from interactive simulations. Additionally, a lot of original apprenticeship learning assume every goal, every reward, every expert have the same reward function. And that's not the case when we have the long trajectory of the human history. When we're younger, we probably want to study hard. When we get older, we want health, right? We involve our reward function along these long trajectories. So in this whole field of apprenticeship learning, online learning, you cover everything. We have the same reward function we can handle pretty well. We have in a group demonstration, there's a different reward function we can also handle pretty well. And involved reward function that also can be handled well for the online apprenticeship learning. But offline, when we start this work, there's nobody have done on the involving reward in the trajectory we pre-collected. So we propose this same framework, and it's actually just presented last month in KDD 25. And so we basically segment trajectories into automatically segment. And for each of the segment, we cluster them, try to based on the cluster, in each of the subsequence, they may have the same reward function. We induce policies from that reward function and reverse iteratively going back to this process until converge. So that's apprenticeship learning. We have shown significantly that our framework can predict what is the expert demonstration's next action much accurate than deep reinforcement learning and even the state of art apprenticeship learning methods. And so the next one is explainable AI. We want AI to be transparent. And you have knowledge distillation, but you train a model, try to understand the model. How about we just saying directly using interpreted model, directly learn the reinforcement learning and throughout the model. So in this work, we have this, I just came back from the HCAIC, that's my student, John Hausteller, have a fuzzy reinforcement learning. Directly, you can induce policy like if-then policy. If this happens, this happens, this happens, then you should do this. And that's a policy students or get carried out during the training, and that's a policy that explainable AI will spell out directly. So I will give you some like basic literature explain the benefit explanation. We human want to know what's going on and then see what is reasonable or not. I can trust the system. And one benefit for us, we think that reinforcement learning actually naturally fit explanation, because explanation, there are two types of explanation. First, we want to say, you suggest me these actions. Why did you, how come you suggest these actions? Another things we care about is you suggest this action, what is it for, right? There's a lot of different kind of explanation. Here is the two aspects. We think reinforcement learning naturally fit. So state mapping to action, that is how come. Reward function, we basically tell them what it's for. And so explanation for the previous, whatever deep reinforcement learning, and we get a rule in the bottom. So it's very not human interpretable. And the fuzzy reinforcement learning, basically we can get a rule like in the top, if then. So if the student have a few hints, if you can solve the problem pretty good, and then you should do that. This is a policy we actually carry out in the system, and this policy very interpretable to human, and human can also change this policy accordingly and directly input the policy back to the system to change how they interact with the students. And so this framework, it allows the human experts' knowledge to go in. So overall, we just summarize, we have this framework is a human and AI interactive. What we want is collaborative. And we want to learn from AI. We know AI empower a lot of things. AI also want to learn from human. And we want a whole framework that not only saying that AI is running in the backend, we want AI and human interact and then have a better action or the reward function eventually that reach more productive interaction. So overall, in this framework, we need considering complexity of the data, modeling, and optimization and evaluation. And our ultimate goal is close the gap, and whatever we run in the lab, we'll be able to make an impact in the real world. Here is the overall that we want to future. It's an individual, we want going up to the system because, for example, in the healthcare, there's a limited bed, right? Not everyone can get all the treatment. And there is a financial kind of money, kind of what we call healthcare cost, copay, every complex factors we have to considering and how we scale up. And also here are my students and collaborators, and this work will not happen without them. Thank you so much.
Thank you, Dr. Chimin. We have a few minutes for questions. So if you have questions, raise your hand and I come to you. All right.
Thank you, Dr. Chai. Very great works.
Thank you.
Awesome. So a couple of questions. First, what's the difference between apprenticeship learning and inverse RL?
Inverse RL is one type of apprenticeship learning.
Oh, okay, so do you use this AL in inference or training or both?
Both. Yes, both.
So how do you scale in inference? So in inference, we need like lots of calculations. So basically, I'm wondering if you can use it for training language models, the way that the OpenAI is training.
So you mean apprenticeship learning for the training the language model? We haven't not using that because generally speaking, we want the expert demonstration, right? And then here for language model, there is no very clear the state and action. If you want to think every next word is action, and then the space is too big. And even our themes, like what we propose, one of the limitation is our action space we can handle is pretty small. It's still binary. So there is a future work for large space, continuous even, like treatment, we don't say give you prescription. We also want to say how long, right? And that's still the future work we need to do.
I see. All right. Thank you. Great
Sure.
works. Yep.
Thank you.
Congratulations.
Yeah, that's a limitation. It's still.
Yes, thank you for your question. Any other questions?
Doctor, you mentioned that in the chart, you showed the physician decision actually have a worse shock rate than the AI agent, right? Is that do you mean that but why you need a physician decision there? And is that means the physician decision need to be helped by the AI agent to get a better shock rate? Is that what I mean?
This graph?
Yeah.
So this one, the physician is not, so we induced like SALSA is one of the preliminary reinforcement learning policy. Just try to copy physicians. Try to like saying here is historical what the physician do and learn from that, and then try to matching what exactly most common things people will do in the. So SALSA, this physician policy is not exactly all this data come from the physician's treatment. And the SALSA, the physician policy, is try to kind of close to behavior cloning, very initial, very naive way of induced policy. So the point here is if you only use naive way of reinforcement learning induced policy, the policy doesn't perform well. Yeah.
Thank you. Any other questions?
Thank you. How the uncertainty is communicated to the human from the uncertainty from
uncertainty. And so communicate with the human, you mean, so how we model the uncertainty in this?
Yeah.
So we, that's a very good question. So uncertainty in this sense, we try to, let me go back to this one. So the reward function is actually when you, why sometimes the inferred reward work better than the immediate reward that ground truth. Everyone reinforcement learning constantly use the reward function. It's because the reward function we use delayed is much more robust, but it's just delayed. Then the immediate reward you get, maybe there's an uncertainty in it. So that's the closest we model that. And I think there are better ways to model. Any others?
All right, we have time for one more question if you have.
I have a very probably simple question about human in the loop system. I think any system probably going to have two problems based on my understanding. The first one is human is slow, right? So, and especially why for the reinforcement learning, why people pick up a computer game, because you do not need to use the real time, right? You can speed up anything inside your simulation. The second problem is basically human also makes a lot of mistakes, right? And rewards are also very, very sparse for reinforcement learning system. And given the human also make mistakes, what do you think about how to handle these two problems?
Very good question. So it's like a human can make mistakes, and that is one of the reasons that when we do the apprenticeship learning, and sorry for jumping around. So when we do the apprenticeship learning, we don't assume why we say human like we involve reward function. We don't assume a human will constantly making the optimal policy all the time, right? It's not only involve policy, it's also in this, when they all in the set, we all want to get to the best school, and some people is more efficient than other people. So in that cluster of sub-trajectories, you still have the best of the best, and then, okay, close to the optimal, but not, or even suboptimal. And that's kind of things why we want to considering that humans do not always making the best decisions. That's why we want to considering that maybe only certain point this human is making the best decision for the physician too. There's certain stage this physician makes the best, but across the trajectory, you should be able to see that when patient at this stage, what's the best treatment you should get. Is this answer your question? Okay, great. Thank you so much.
Thank you again, Dr. Ximing.
Thank you.
Thank you for your questions.